All right, good morning, everyone. Here is our Quiz 6 review. First up, I'm just starting you off with determining which distribution is going to be binomial versus geometric, and then we're going to calculate probabilities. So just to remind you of the difference, right? With binomial, here we're looking at a fixed number of trials. So for example, I flip a coin 10 times. I have a fixed number of trials, right? I've flipped my coin 10 times. And then what I'm interested in calculating is I'm interested in calculating certain outcomes. I could have 0 tails. I could have all 10 that are tails, or it could be something in between. Okay, for geometric, we have no fixed number of trials. We keep going until we achieve a certain end result. So we keep performing trials until we get to a success, or sometimes we see that we're getting to a failure instead. All right, so let's read through this first problem and see what we got. So here we have 30% of students who drive to campus carry jumper cables. Your car has a dead battery. You don't have jumper cables, so you decide to stop students who are heading to the parking lot and ask them if they have a pair of jumper cables. Find the probability. All right, so when I look at this, well, what I'm hearing is that, well, there's no fixed number of trials. It's not like I'm stopping 10 kids, right? It doesn't give me a fixed amount of trials. It tells me that I'm going to keep stopping students until I get to the pair of jumper cables. So right away, I know that it's going to be geometric. There's no fixed number of trials. We're going to keep going until we get to that desired end result. So here in part A, I'm saying, well, what's the probability that we're successful on the first try? The first person stopped has jumper cables. Well, I know right away that's saying that we are initially successful. We're successful on that very first try. So I know what that should be. I know the probability of being immediately successful is just going to be 0.3. I'm told that from the very beginning, that 30% of students who drive have carry jumper cables in their car. So if I'm initially successful, I'm successful on the first try, it's got to be 0.3. But if I go back to the calculator keystrokes, here I would be saying, well, so geomet, and then PDF, geometric PDF. And then here I say, well, 0.3, that's my probability of success, and I want to be successful on that very first try. Just up here, I'm going to write that the p-value is 0.3. The q-value, failure, would be 0.7, complement of success. So how do I get there? How do I get there in my calculator? I want it to confirm that 0.3. So I hit second vars. I go all the way down to geomet PDF. Okay, my p-value 0.3, and I want to be successful on that very first try. So see how it confirms that 0.3. 0.3. All right, next up it's saying, well, out of 3 people being stopped, no one has jumper cables. So what that's really saying is that the success, it does not occur on trial 1, 2, or 3. It occurs on that 4th attempt or afterward. Let me write that. So our success, finding a pair of jumper cables, it's going to occur on that 4th attempt or afterwards. So I can say that x is equal to, well, it could be the 4th try, the 5th try, the 6th try, or so on. So whenever I see that, I think, oh, I gotta go through my complement. I have to do 1 minus the probability of being successful on the first try, the second try, or the third try. So I'm going to use the CDF function this time. So 1 minus geometric, so geomet, CDF, right? That's my fancy shortcut. The p-value is 0.3, but I'm looking at being successful on the 3rd try or less. So here again, this is saying 3rd try or less. All right, so if I plug that into my calculator, 1 minus second vars. I'm going down to geometric CDF, right? That's my cumulative function, so right there. And I'm saying my p-value is 0.3, and my x value, I'm going to be successful on that third try or less, right there. So it gets me 0.343. Didn't even have to round. It is exactly 0.343. Okay, so that would capture being successful on the fourth try, the fifth try, the sixth try, or anything after that. So again, I just had to go through the complement. I did 1 minus the probability of being successful on the first, second, or third try. All right, for C, it's saying less than 3 students must be stopped to obtain jumper cables. So here we're saying less than 3. What does that encompass? That means it could be exactly 1 or 2 tries to get to that desired end result. Just underline. Okay, so 1 or 2, well, I could use my cumulative function here too. I could say geometric, so geomet CDF 0.3, comma 2, right? Because that's telling me on the second try or below. So let me pull this up. So second vars going down to geometric CDF, enter. So 0.3, comma 2, right? Because that's 2 or less. 2 tries or less. So I get 0.51. Okay, more than 3 students must be stopped to get jumper cables. So if it takes more than 3 students, success could come on the 4th try, the 5th try, the 6th try. We've actually already solved for that up here in B. It's just the wording that's different. So up here in B, it's saying, well, out of 3 people stopped, no one has jumper cables. So it's telling us you're not successful on the first, second, or third try. Your success comes on the 4th try or afterwards. And here it's saying, well, it's going to take more than 3 students to get to those jumper cables. It's, saying the same thing. Success will come on the 4th, 5th, 6th, and so on try to get to the jumper cables. So here again, it's the same as B. So I get 0.343. All right, mean and standard deviation. Well, it's geometric, so we know that the mean is 1 divided by P. So 1 divided by 0.3 will get me about 3.3333. So 3 1/3. Okay, so my mean, let me just box that. My mean is about 3.3333, and I know we're talking about students. So on average, we'd have to ask about 3.3333 students until we can get to our desired result of getting jumper cables. Okay, but with what measure of variability, right? We need our standard deviation to tell us how far a typical value should fall from its mean. So here for geometric, big square root, Q divided by P squared. So here I'm plugging in big square root 0.7 over 0.3 squared. So that's going to get me about 2.7889. So standard deviation is about 2.7889 students. So again, right, we need to make sure that we can make sense of all of this. We need to give it some context. So if I write a short statement, I could say something like, well, on average, you'd have to ask about 3.3333 students to be able to get our jumper cables, I'm going to abbreviate right there, with a standard deviation of about 2.7889 students. Okay, so we're saying, well, this is what we would expect to see on average in the long run. And then here's our indication of how spread out our distribution would be in relation to its mean. All right, problem 2. I'm going to slide it up just a little bit. All right, so decide which distribution is appropriate, binomial or geometric, then calculate the probability. So suppose 30% of students who drive to campus carry jumper cables. Your car has a dead battery. You don't have jumper cables, so you run into the nearest classroom with 20 students and ask if anyone has a pair of jumper cables. So the setup is pretty similar to what it was in part 1. What's different is that now we're asking 20 total students. So what we're interested in is, well, what's the likelihood that none of those students carries jumper cables? What's the likelihood that all 20 carry jumper cables? Or more likely, something in between the 0 and the 20. But we know that those are all of the possible outcomes that could play out here. So again, that triggers for me that this is a binomial situation. My n value is 20. That's my total number of trials. My probability of success is 0.3. Failure is 0.7. And x could be that none of them have jumper cables. 1 has jumper cables. 2 has jumper cables, all the way up to all 20. So you hear me say this all the time, right? It could be all, could be none, could be something in between. So in A, we're calculating at most 6 students have jumper cables. So we're saying, well, at most 6, at the very most 6. So it could be 0, could be 1, could be 2, could be all 6, right? Something in that span. So here I can use my cumulative function for a binomial distribution. So I can say binom CDF. My n value is 20. My probability for success is 3. And I'm looking at exactly 6 successes or less. And that's crucial, 6 or less. So in my calculator, I'm doing second verse. I'm going down to my binomial options. So right in here, and I want CDF. So my n value is 20. My probability of success is 0.3, and I'm looking at 6 successes. 6 students carry jumper cables or less. So here I would get about 0.608. That would be my probability of this scenario playing out. So 0.608. All right, now I'm saying exactly 8. So x is exactly 8. So now I can use my binom PDF function because I'm solving for something exact. So binom PDF 20, 0.3, 8. My n value, 20 trials. My probability of success, 0.3. And here is my exact count of success, 8. So here, second verse. Okay, that takes me to my distributions. I'm going down to binom PDF this time, and then I'm doing 20, 0.3, 8, and I get 0.1144 about. All right, next one, we're saying at least 10 students have jumper cables. So here x could be exactly 10, could be 11, could be 12, all the way up to 20. So whenever I see that, I always think, I'm going to go through my complement. So I'm going to do 1 minus the probability that we're successful on here, that we have 0 successes. We have 1 success, 2 successes, all the way up to 9 successes. So then I can use 1 minus binom CDF, cumulative function, 20 trials, probability of success, and I'm looking at exactly 9 successes or less. 9 or less. Okay, so if I type that into my calculator, I should end up with 0.048 about. All right, for D, between 4 and 7 inclusive have jumper cables. So that means it could be exactly 4, x could be exactly 4, exactly 5, exactly 6, or exactly 7. So 4 through 7 kids carry jumper cables. So how could I get to this? Well, I can still use my cumulative function, right? I can use binom CDF and solve for 7 down to 0, and then I can take away 3 down to 0. So let me flesh that out again. So I can solve for the probability of 0, 1, 2, all the way up to 7. And then I can take away the probability of 0, 1, 2, or 3, like that. So I'm going to use the binom CDF function to capture those outcomes. So here I'm saying binom CDF 20, 0.3, 7. So this would give me the probability of exactly 7 successes. Exactly 7 students carry jumper cables in their car or less. Okay, but then I want to get rid of everything that is before the 4, right? So I want the 0 through 3. I want to get rid of that. So I'm going to take away binom CDF 20, 0.3, 3. So I'm taking away 0 through 3 successes. This is 3 or less. Okay, so take a moment, plug that into your calculator, and check to see that we match. Okay, we should get about 0.6652 as our overall probability right there. Okay, and then lastly, what's the mean? What's the standard deviation? So out of 20 students, how many do you expect to have jumper cables, right? That's telling us find the mean. And then with what indication of how spread out the data is in relation to the mean. So our mean for binomial, we're doing n times p. So I'm saying 20 times 0.3. So we'd expect on average, right, in that sample of 20 students, we would expect to see 6 of them to have jumper cables. And then with what measure of spread? Standard deviation. So square root of n times p times q. So square root of 20 times 0.3 times 0.7. So that should give us an approximation of 2.0494 students. Okay, so again, means nothing if we can't actually flesh it out in real words, right? Normal language. So here we can say, in a sample of 20 students, on average, we would expect about 6 students to carry jumper cables, with a lovely standard deviation of 2.0494 students. All right, so we should be pretty good at our binomial and geometric review. Okay, let's flip to the next page. All right, here we go. All right, so first up, I'm saying a computer salesperson works on commission and receives a fixed amount for each computer sold. Suppose for a given month, the probability distribution of X equals the number of computers sold. So here we're looking at a basic, discrete probability distribution. It's what we started with in this whole unit. So we started by looking at a discrete probability distribution. So we know that what X can take, these are nice, clean numbers, right? These are nice, whole, clean values for our possible outcomes. And we're looking at number of computers sold, right? Could be exactly 0, could be exactly 1, all the way up to all 7. So if this is a true probability distribution, it's showing us all possible values that our random variable could take, 0 through 7 computers sold, along with their corresponding probabilities. So we should remember that each of these values has to actually be a probability, right? We want to check for, essentially, for any typos. We shouldn't have anything negative. We shouldn't have anything more than 1. A probability has to always be between 0 and 1. 0, never going to happen. 1, always going to happen. We are usually somewhere in between. Okay, and then we also know that since it's representing all of our possible outcomes, collectively, all of those probabilities, they have to add up to 1. Let me write that right here. Our probabilities must add up to 1 total. So if I'm first asked to find that missing probability, I'm really doing 1 minus all of these probabilities combined. So I end up doing 1 minus 0.87, and that missing probability is a 0.13. Okay, find the probability that x is less than or equal to 2. So sells 2 computers or less. So here I'm just adding up these 3 outcomes. So 0.01, 0.09, and 0.12. Gets me to 0.22. Right? That is my likelihood of selling exactly 2 or less. Okay, write the event sold more than 4 computers in terms of x, and then find its probability. So more than 4 computers would be 5, 6, or 7, right? So we're saying, okay, well, x equals 5, 6, or 7. So how could I write that as an inequality? Well, I can say the probability of x, well, it has to be more than 4. And if I add these up, I get 0.19. That's probably how I would write it, but I can think of another way I could write it, and it would really mean the same thing. So if I'm saying more than 4 computers, that means it could be exactly 5 or greater. So I could have also written it using this alternate notation. So I could say, really, what's the probability that x is greater than or equal to 5? And I would end up getting the same exact thing. So both of those notations work. Doesn't matter to me. All right, next up is an expected value question. An expected value is really the same thing as calculating the mean. Okay, what's different is really context. So with expected value, we're pretty much looking at something where we are, gaining or losing money. And when we're looking at anything that has to do with the lottery or gambling, we are usually out, because if we lose money, then we know that the lottery, we know that the casino, they win money, they gain money from us. So we expect to see negatives when we're talking about expected value, when we're talking about, fundraising, lotteries, gambling. All right, so here is our setup. We are playing a raffle. Sells 1,000 tickets total, $5 per ticket. We have one $500 prize. We have 5 $100 prizes, 10 $50 prizes. Find the expected value. Write a statement to summarize what this represents. Okay, so first we want to look at all of our prizes. So even if we win that first place prize of $500, we still paid $5 per ticket. So this part is pretty crucial, that $5 that we're putting out per ticket. Let me slide this up a little bit. So even if I win $500, I've paid $5 to play, so really I stand to gain $4.95. Okay, my next prize is $100, but again, paid $5 to play, so that means really I'd be taking home $95. Okay, that last prize, $50, right? Again, take away the $5 we paid to play, so $45. So these are all of our winning scenarios right here, right, where we stand to gain something, but we could also just be out. We could also just lose and be out $5. Okay, and then I need to go through and I need to look for all of the probabilities. Well, I have one of these prizes, so I have a 1 in 1,000 chance of this scenario playing out. Okay, for this next prize, I have 5 of them, so I have a 5 in 1,000 chance of that playing out. I'm going to keep a common denominator, so I'm just going to keep everything out of 1,000. I'm not going to reduce that down. Okay, for this prize, we have 10 of them, so I have 10 out of 1,000. Again, I'm not going to reduce it down. I want everything to have that denominator of 1,000. So now when I skim through, I really have 16 total prizes, right? 16 total opportunities to win. So if I take 1,000 and I take away 16, then I have 984 losing tickets out of 1,000. So again, my probabilities here still have to represent all of my total scenarios that could play out, so they have to add up to a total of 1. Okay, so now when I'm getting to my expected value, it is the same thing as getting my mean. So all I'm doing is I'm looking at the sum of these products. Product just means multiply. Sum means we add. So I'm taking my prize here, 495, and I'm multiplying by its relative frequency or its probability. And then I'm going to add that to the product of 95 times its relative frequency or probability, and then I'll add that to the same thing here and the same thing here. So I'm taking 495 multiplied by 1 over 1,000, adding that to 95 times 5 over 1,000, adding that to 45 times 10 over 1,000, and then adding that to the negative 5 times 984 out of 1,000. So let's type that in together. I want to make sure that we match and we know how to type it in. So let me just make sure I'm out of the blind spot. All right, here we go. So I'm saying 495 times 1 over 1,000, okay, plus 95 times 5 over 1,000, plus 45 times 10 over 1,000, okay, minus 5 times 984 out of 1,000. And there we go. Negative, right? We expected it to be negative because if this is a fundraiser, they want to win money off of us. So 3.5, negative 3.5. So in context, we're saying, well, this is what we would expect to play out. So on average, per ticket purchased, we stand to lose $3.50. Okay, so per ticket purchased, on average, this is what we expect. We expect to be out $3.50. All right, next up, we're back to our z-scores and our normal distributions. So I just want to remind you, you've got to take out your z-score chart. That will be helpful. All right, so here we have a vending machine that automatically pours soft drinks into cups. The amount of soft drink dispensed into a cup is normally distributed, so we know it has that bell-shaped curve to it, with a mean of 9.5 ounces. I'm just going to underline that. And a standard deviation of 0.25 ounces. So off and off to the side, you'll see us just kind of summarize it as big N for normal. And here's the mean of 9.5, and here's the standard deviation of 0.25. So here's my mean, and here's my standard deviation. All right, the machine has just been loaded with 1,000 10-ounce cups. How many of these do you expect will overflow when served? So if we're saying overflow, what does that actually mean? So if it overflows, that means it's really going to fill beyond that 10-ounce capacity. Right? Something that's more than 10 ounces. So if I visualize this, here's my normal curve. Here's my mean, right? That's where my z-score is 0. And my mean in this context is 9.5 ounces. So if I put 10 ounces down, let's say I just put it about right here. Here's my 10 ounces right there. And I'm saying overflow, I'm looking at anything that is more than 10 ounces. That's what I'm solving for. So the first thing that I need to do is I need to get to what the z-score is right here. So I know the mean, I know the standard deviation. So my mean is my observation, sorry, my z-score is my observation minus the mean over the standard deviation. So that's my z-score. Z equals observation minus the mean over the standard deviation. So if I plug in, my observation here is 10. 10 minus 9.5 divided by 0.25. And I should get a z-score of exactly 2. So z-score here is exactly 2. So I'm trying to solve for the proportion first that falls in this region. What is the area of this part right here? So I know that when I use my z-score chart, it's always giving me the region below it. So to get to the region above it, knowing that the total area under this curve sums to 1, then I do 1 minus what is to the left of a z-score of 2. So if I look at my chart and I look up a z-score of 2 right here, I see 0.9772. So what that's telling me is that this area to the left is 0.9772. I want to the right, so I'm doing 1 minus what was to the left. So then I get 0.0228. So that is the area under the curve right here. That is the proportion that is to the right of that z-score of 2. So if I'm trying to see, well, if I'm loading the machine with 1,000 cups and I'm interested in how many do you expect will overflow, well, I'm just multiplying. So I'm taking those 1,000 cups and I'm multiplying by the proportion that would exceed that capacity of 10 ounces, which is the 0.0228. So that's going to get me 22.8. And I can't have a portion of a cup. So my instructions for you right now are just to round to the next integer value. So here you would just follow your normal rounding rules. That 0.8 will pull it up to 23. So we'd say that we would expect about 23 cups to overflow. Okay, next up, let me push that up. One more and we're done. All right, your company manufactures screws. The length of the screws are normally distributed with a mean of 4 inches and a standard deviation of 0.03 inch. You are filling an order for 100,000 screws. You agree to replace any whose lengths differ from 4 inches by more than 0.04 inch. About how many ball bearings will you have to replace? Okay, so here, first off, we should be talking about screws. So looks like Miss Crystal made a little typo. We're looking at screws. Let me fix that. Okay, so here again, I'm just going to summarize to the left what was the mean. The mean is 4, and the standard deviation is 0.03. Mean and standard deviation. Okay, so then what is it saying that we're going to replace in terms of the screws? So we'll replace screws, right, that deviate from that mean by more than 0.04 inches, essentially. So I'm really looking at, well, what is 4 plus or minus 0.04? So that would give me 3.96 inches or 4.04 inches. So I'm just adding 0.04 and I'm subtracting 0.04. So what that's saying then is that we will replace any screws that are shorter than 3.96 inches and longer than 4.04 inches. Okay, so it's a nice quality control situation. So we're saying we will reject anything that is shorter than 3.96 inches and longer than 4.04 inches. Anything in between is perfectly fine. It is acceptable. So here, if I visualize it first, right, here's my normal curve. Here's where my mean is. That's where the z-score is 0. And our mean in this context is 4 inches. Okay, so I know that maybe roughly here to here, right, this is where we deviate by that 0.04 units, inches. So we're saying, okay, well, if we get something that is 3.96, if it's less than 3.96, we're going to reject anything over here. And if it's more than 4.04 inches here, we're going to reject those two. So we want everything to be safe within here to here. Out in here is what we are going to reject. So I need to find the proportion that falls in that region. So I need to, again, go to the z-score. So if I look at the first z-score, z equals 3.96, take away the mean of 4, divide by the standard deviation of 0.03. So here, nearest tenth, I get negative 1.3 for that z-score. So z equals negative 1.3, about. Okay, and then if I look at the other one, I should already have an idea because they're equidistant, right? They're both 0.04 inches from our mean of 4 inches. So it should have the same magnitude, the same distance from the mean when we're thinking of its z-score. So I should know right away that it's going to be a positive 1.3 for the z-score. But let's just double check. So if I plug in 4.04 and take away 4 and divide by 0.03, go ahead and type that into your calculator. We should see 1.3. Okay, so again, we're solving for the proportion of screws, right, that would fall in these two regions. So if I look at my z-score chart and I look up a negative 1.3. So here's my negative 1.3, 0.0968. So my area right here to the left is 0.0968, right here. Okay, that's what my chart is always telling me, is the region that's to the left. So I also should know that if I'm looking at z-scores that have the same magnitude, so same distance from the mean, so if I'm looking at the region that's to the left here and the region to the right here, these areas should match. So right here will also be 0.0968. So if I'm looking at my total area, I just have to add those two together, 0.0968 plus 0.0968, and that gets me 0.1936. So that's telling me that the proportion of screws that would be rejected, right? So it's saying, well, it's almost 19% of screws would be rejected because here they're too short or here they're too long. And then we're saying, well, imagine that we're looking at an order that's 100,000 screws. Well, how many are we going to have to replace? How many are we going to have to reject? So we're taking that 100,000 and multiplying by the 0.1936. And that will give us exactly 19,360 screws that would need to be replaced. All right, so a good quality control situation. All right, I hope that everything is making sense. If you guys are having any questions, please make sure that you submit them to the link that I have on my website or email me directly. That is always an option. That is always fine. I hope you guys are doing really well. I miss seeing you every day. I hope to see you guys soon. All right.